In the today's class, we'll find out, we'll discuss the brief information about the Hall effect in semiconductors. What do you mean by Hall effect? And how does Hall effect is significant in case of semiconductors? So if you take this particular diagram here, a semiconductor material is connected to the external battery along X direction. It is connected to battery so that current will flow along X direction. If you apply the magnetic field along Z direction like this, then the moving electrons inside the semiconductor will be pushed downwards. Okay, and that effect is called as Hall effect. That means if you apply the electric field and magnetic field perpendicular to one another in a semiconductor, then along the direction perpendicular to both this electric field and magnetic field, and voltage is going to be developed, and that voltage is called as Hall voltage. The effect is called as Hall effect. So when a magnetic field is applied perpendicular to a current carrying conductor, a voltage is developed across the specimen in the direction perpendicular to both the current and the applied magnetic field. This phenomena is called as the Hall effect. Okay, so it was discovered by Hall. That's why his name is used to indicate this phenomena. The voltage so developed is called as Hall voltage. You look at the diagram, it is the indicative diagram to understand the Hall effect. A semiconductor piece of material is connected to external battery and current is flowing like this. Okay, electrons are flowing in opposite direction. Then this is actually the applied electric field. If you represent this along X, Y, Z direction in a Cartesian coordinate system, along X direction, an electric field is applied so that electrons are going to flow along the direction of applied electric field. Suppose you apply the magnetic field along Z direction. Let us take HZ is the electric field, magnetic field applied along Z direction, that is perpendicular to the flowing electrons. Okay, then what happens? This magnetic field applies some force on those charges and it will push the electrons towards the Y direction. Okay, so Y direction is adana push ಮಾಡ್ತದೆ. Because of that, the moving electrons along X direction will try to move along Y direction. Some of the electrons will move along Y direction. Otherwise, some electrons will be accumulated on the bottom part of this conductor or semiconductor. Because of that, the upper surface becomes the positively charged surface, the lower surface becomes negatively charged surface. Because of this charge distribution, you will get an extra voltage inside the semiconductor, and this voltage developed across Y direction is called as Hall voltage, and this phenomena is called as Hall effect. Simply you can remember the Hall effect. If a magnetic field is applied perpendicular to the current carrying conductor or semiconductor, a voltage will be developed across the specimen, across the conductor, in a direction perpendicular to both current and magnetic field. Okay, so this phenomena is Hall effect. So remember, along X direction, electric field is applied. Along Z direction, magnetic field is applied. Then the extra voltage is going to develop along Y direction. That is perpendicular to both the current and applied electric field. That is how we can understand this concept of Hall effect. This Hall effect can be observed in conductors also, in case of semiconductors also. You cannot observe this in insulators because insulators cannot carry the current. That's why it is observed in conductors and semiconductors. Next, let us see what is the theory of this okay. So this is how you can understand the Hall effect properly. Then to explain this further, Consider a slab of material subjected to an external electric field Ex along x-axis and the magnetic field Hz along z-axis. Already I have explained you. A material is considered, which is a slab, which is a slab-shaped material, three-dimensional material, in which the external electric field, a battery is connected to that slab, which is nothing but the external electric field Ex is applied along x direction, so that current is going to flow along x direction, and a magnetic field is applied along z direction, that is perpendicular to the flowing current. As a result of the electric field, the current density Jx will flow in the direction of Ex. So when you apply the voltage by means of electric field, the current will flow. We will consider the current density Jx, that is nothing but current per unit area of cross section. Jx will flow through the x direction in the material, in the x direction. So Jx is nothing but I divided by area A, current per unit area. So Jx is taken because current is flowing along x direction. Okay. Let the current be carried by an electron of charge -e. Okay. Let us take the current is only due to the charge, that is electrons, not because of the holes. Okay. So total current flowing in the material is due to the majority of electrons. And each electron is having the charge -e. In the next step, we'll consider the external magnetic field Hz applied perpendicular to current. That will exert a transverse magnetic deflecting force on the electron, which causes the electron to drift downward to the lower edge of the specimen. The magnetic effect of current has to be considered. When charge moves inside the magnetic field, what happens? It will deflect towards the perpendicular direction. Okay. And the direction of deviation or direction of deflection is given by Fleming's left hand rule. Already have studied. So if magnetic field is applied along z direction, the flow of electron is in x direction, then deflection of electron is going to take place along y direction. So these three are perpendicular to one another. So those electrons will push it towards the lower edge of the specimen or lower surface of the specimen. Consequently, the lower surface of the slab collects large number of negative charges and upper surface becomes positively charged side. So what happens? More and more electrons will be pushed towards down surface, and there will be deficiency of electron on the upper surface. So that leads to positive and negative charge distribution. So that leads to the potential difference. Okay, there will be more potential at upper surface, less potential in the lower surface, because it is at negative potential because of the collection of electrons. This potential difference provides or that produces an voltage called Hall voltage. This excess of negative charge on the lower edge and the corresponding excess of positive charge at the upper edge creates a transverse electric field. Okay, and that transverse electric field will be in the direction of y, and that is denoted as Ey, which is called as Hall electric field, which opposes the transverse drifting of electrons. Again, it will oppose the flow of electrons along x direction. So there will be competition. The applied external electric field Ex will push the electron along x direction. The magnetic field will create a transverse electric field Ey, which is called as Hall electric field, which is along y direction. And these two will interact. Because of that, there will be slowdown of electrons. The velocity of the electron will decrease. Okay, so there will be more and more accumulation of electrons on the down surface, and that will try to stop the flow of electrons along x direction. So this is basically called as Hall effect. And this Hall effect is observed in conductors and semiconductors. Okay, this is how we can understand the Hall effect. Next, what is the relation between this current density Jx, the magnetic field Hz, and electric field Ey? What is the relation between them? It is given by the Hall voltage developed Ey, which is equal to minus Jx Hz divided by Ne, where Jx is current density along x direction, Hz is magnetic field applied along z direction, divided by N is number of electrons per unit volume of the conductor, E is charge of the electron. Okay, so here you can replace this minus 1 by Ne as a Hall coefficient RH. Therefore, the effective Hall electric field Ey, which is equal to RH Jx into Hz. This is the relation connecting the Hall electric field, the applied current density, and applied magnetic field, and this RH is acting like a proportionality constant. And this RH is given by minus 1 by Ne, which is called as Hall coefficient. And here N is the number of charge carriers, electrons in case of conductors, electrons or holes in case of the semiconductors, N-type and P-type semiconductor. Based on that, the majority charge carriers may be electrons, may be holes. So these are, N is the number of charge carriers per unit volume of the semiconductor, and E is charge of electron, charge of one electron. Here this negative value of RH, this RH is observed to be minus, negative. It indicates that current carriers are electrons. If the charge carriers are holes, RH is going to be positive. Okay. For P-type semiconductors, the majority charge carriers are holes. Then this Hall coefficient is going to be plus 1 by Ne. Okay. So RH is positive for P-type semiconductors and RH is negative for N-type semiconductors. So this Hall coefficient may be negative or positive in case of semiconductors. But in case of conductors, Hall coefficient is always negative, because in conductors, the majority charge carriers are only electrons. But in semiconductors, based on the type of the semiconductor, whether it is P-type or N-type, the majority charge carriers may be holes or electrons. If majority charge carriers are holes, this Hall coefficient RH is going to be positive. It will be plus 1 by Ne. If it is negative, then it means that the material is N-type semiconductor. Okay, so vice versa. So what are the applications of Hall effect? The Hall effect measurements provide the following information about this Hall effect. So first application is the sign of charge carrier can be determined. Okay, whether it is electron or hole, based on the direction of the Hall effect development, otherwise Hall electric field development, you can find out whether the material is N-type semiconductor or P-type semiconductor. Second application is the carrier concentration can be determined. That is, number of charge carriers per unit volume can be determined if you know the Hall coefficient for a material. Okay, by measuring the applied electric field, applied magnetic field, you can find out the value of the N. Value of N you can find out. Then the mobility of charge carrier can be measured directly. Mobility can be measured. What is the expression for mobility? So mobility is nothing but drift velocity per unit electric field. Okay, and also current density J is equal to Ne into Vd, or you can define the current density J, that is according to Ohm's law, you can find out the mobility relation as Ne by sigma. So already I have studied in free electron theory of matter. Using that, you can find out the mobility of charge carriers using Hall effect. Then we can decide whether the material is metal, semiconductor, or insulator. Okay, based on the direction of Hall electric field developed, you can find out whether the material is metal, semiconductor, or insulator. The higher the magnitude of Hall voltage, it means that the material is a metal. Intermediate value of Hall voltage indicates that the material is semiconductor. If there is no Hall effect, it means that the material is insulator. Okay, metal gives higher magnitude of Hall voltage, Semiconductor gives intermediate value of Hall voltage. Based on that, you can decide by Hall effect experiment, you can find out whether the material is metal, semiconductor, or insulator. Then from the knowledge of measured Hall voltage, the unknown magnetic field can be measured. Okay, if you know the applied electric field, you can measure the Hall voltage, then you can find out the value of Hz, that is magnetic field, which is applied to produce the Hall effect. Okay, if Hall constant or Hall coefficient is known to corresponding material, then you can find out the value of Hz. This is how you can measure certain properties of the material by doing the Hall effect experiment. Okay, so this is about Hall effect in semiconductor.